It's another example of a max-min problem. You'll notice in this case I have the parabola y equals 4 minus x squared, and specifically I have a cone that is bounded by this parabola, basically meaning that the radius has to lie somewhere along that parabola, and I want to try to find the maximum possible volume of that cylinder, or in this case, I'm sorry, of that cone. And if you think about what happens, as I make this thing taller, you would expect the volume to increase, except the radius gets smaller, which makes it seem like it would reduce the volume. If I decrease the height, you'll notice the radius gets bigger, but of course that means it will be shorter. And so the question is, what are the perfect dimensions to create the largest possible volume? Well, let's take a look at this. I'm going to take a look now at the volume of a cone problem. Same thing as usual. You want to start out with some kind of a diagram of what's happening. And in this case, I have this cone. I have the function y equals 4 minus x squared bounding this cone. In other words, the cone is drawn somewhere in here with the base along that curve and the vertex at the origin. And normally the second thing I do here is I write what's referred to as the constraints equation. And interestingly, I don't have a whole lot of work to do here because the only thing that constrains what's happening in this problem is this parabola, which was this function right here. So interestingly, I was already given the constraints equation, which seemingly makes things a little bit easier. Now, from this point, where do I go? Well, first of all, I want to try to figure out what is going to be maximized or minimized and write a function for that. So if you remember, the problem said that I'm going to maximize the volume. Okay? So you want to write a formula for that. In this case, we know that volume is equal to, this thing comes to a point. So the volume is basically going to be 1/3 the area of the base, which I'll represent with a capital B, times the height. Of course, the area of the base, instead of a pyramid, is actually a circle here. So that's going to be pi r squared h. And that's hopefully a formula that you remember, 1/3 pi r squared h. Hopefully a formula that you remember from geometry from last year. So 1/3 pi r squared h. Problem. I'm using an x and y axis here. I want to write my formula using my x and y variables. And so I have to figure out how to write the radius and how to write the height using those variables. If you take a look over here, I don't know what the radius or the height is. It's something lying along this curve right here. And in fact, this point right here defines everything. I'm going to refer to that point using variables because it varies. The radius is different depending on whether or not I move that point up or if I move that point down. So I'm going to label that point x, comma, y. And I'm going to use that x and y variable as my constraint values in this equation to write my function over here in terms of x and y. So volume is equal to 1/3 times pi times the radius squared. Notice the radius here goes side to side. That's an x value. So it's going to be x squared. The height of this thing is the y variable. So 1/3 pi x squared times y. And of course I can simplify that by removing parentheses. I don't want a function written in terms of both x and y. I want it written in terms of either only x or only y. That, ladies and gentlemen, is where the constraints equation comes into play. I know that y is equal to 4 minus x squared. I can replace it with 4 minus x squared and write this using only x variables. So I have the following function. It's 1/3 times pi times x squared, and I'm actually going to not write the parentheses this time, times the y value, which I'm going to be replacing with a 4 minus x squared. All I've got to do is find the maximum or minimum value of that function. Now, I haven't drawn this on my calculator yet, but I looked at it earlier. The graph does something kind of like this. If you notice, you have an x squared that'll be multiplied by an x squared. It's actually a function, it's a fourth power function. So I can do different types of things to try to solve this. I can solve this algebraically. I'm also going to show you how you could solve it using a graphing calculator as well. But the basic idea is we want to get that value right there. And actually, in calculus, you'll learn how to solve this algebraically. In this case, I'm actually just going to show you this on a graphing calculator. So I'm going to switch over to the graphing calculator, and I'll be back then to finish the problem up in a second. I've entered the function that I want to maximize into my graphing calculator, and I already set this up ahead of time, but I have my window here, and the volume's actually not going to be very big, so I'm setting my x between, you could do 0 and 5 or negative 1 and 5. I want to see the axis here. I set my y also between 0 and 5, or actually in this case negative 1 and 5. And I'm going to go ahead and graph this thing. You see the graph looks like this. I'm trying to find this value right here. As you can see, this is not a regular parabola graph, so I can't just use the vertex formula to find that maximum value. When you're in calculus, you'll end up learning how to find where the slope of the tangent line is equal to 0 up here. That would basically be a horizontal line, and that would tell you where your maximum is. For right now, we don't know how to do that, so the only thing you can do is use the tools on your calculator. Your graphing calculator has 5 buttons across the top that have to do with graphing functions. And in particular, you'll notice in yellow, there's a button that says Calc, and that lets you calculate different things about your function. So if you hit the second key, and then you hit the Calc button, you'll see there are different things like you can find zeros or maximum and minimum, those kinds of values. Numbers 6 and 7, that's a derivative and an integral from when you take calculus. 5, you can find the place where graphs intersect each other. In this case, of course, we want to find the maximum value, so we're going to pick choice number 4. And what it's going to do, you'll see here that it says left bound. Basically, your calculator is going to guess a solution here. Okay, your calculator, surprisingly, does not actually know algebra. So basically, you have to tell it about where on the graph the answer is going to be. So it tells you to click somewhere to the left of your maximum point. Also, sometimes there are multiple maximum and minimum values, and so this helps your calculator figure out which one to look at. So I'm going to hit enter. Now it says right bound, so I'm going to scroll. Again, I'm using the arrow keys here. I'm going to scroll somewhere to the right of that maximum point, and I'll hit enter again. It's going to ask for a guess. If you have a hunch about what the answer is and you want to make the process faster, you can fill something else in there. Usually if you just leave the guess and hit enter, it'll be fine. And you should get a value. You can see we have an x value of about 1.142. You can see that we have a y value here of about 4.188. If you remember from my original diagram, in the original diagram, which you can see right here, the x value is the radius. And remember that we're actually maximizing this volume function here, this function right here. And so actually the output value, the y value of that is actually going to be the volume. So the volume here is approximately, to go back to the book here, volume is approximately 4.188. And by the way, this is more easily found using calculus, but that x value there, that's actually radical 2. So if you substituted radical 2 back into the function, you could get the exact answer. But that's the solution to this max min problem and how to estimate it on a graphing calculator.